my lectures. Greetings to everybody. The plan of the lectures is the following. First of all, I will recall the structural theorem, the main result that was the conclusion of the previous lecture. Then I will describe classes FC0 and FC1. 4 is odd here, and will give an additive decomposition theorem. In a sense, the starting point for the finiteness theorem. Then I will deduce finiteness theorem from the additive decomposition theorem. Then I will go back. The additive decomposition theorem is a crown of many efforts, a summit of a high mountain, and I go to the foot of this mountain and deliver constructive definition of the simplest class of cochains we use, so-called simple cochains. And there are two major tools for the study of cochains, or two major properties, or better to say two major properties. One major property is Phragmen-Lindelof theorem for cochains. And another major property is decomposability of the cochains into super exact asymptotic series. This latter subject is the closest to the semester in Toronto, and I will discuss it in the next lecture tomorrow. And the plan for today is this one. I recall you what are maps to and from. These maps are related to saddle nodes. A saddle node has one contracting manifold, which is holomorphic, and a central manifold, which is real and not generally holomorphic. So the Yulij map of the real saddle node extended to the complex domain is the following composition, reading from the right: a normalizing cochain for a parabolic germ. A normalizing cochain gives rise to quite a new class of objects, cochains instead of functions, and they will be thoroughly studied in what follows. The next factor is delta standard. You may think about it as of exponential of -1/x, classical flat function. In fact, it is composed with some with some semi-regular map, but this is not so important. And G is a holomorphic germ at a fixed point 0, not necessarily real on the real axis, but with positive derivative at 0. And the mapping from is inverse to the mapping to the central manifold. So exponentials in delta standard give rise to exponentially decreasing discrepancies of the monodromy map of polycycles, and this is the source of the most difficulties in the study of problem. So structural theorem claims that the monodromy map of a polycycle of an analytic vector field is a composition of the maps to, from, for real saddle nodes, and of almost regular germs that are real on the real axis. The latter ones come in particular from hyperbolic saddles of analytic vector fields, of real analytic vector fields. And second, they are part of the delta standard, of the standard map for a saddle node. In order to grasp the composition of these maps, almost regular to and from, it is useful to combine a graph, a function, characteristic of a composition. Any map in the product of the maps almost regular to and from is a graph of a function over a segment of length 1. These segments follow in the same order then as the compositions do. The segment corresponding to an almost regular map element of R is just horizontal. The segment corresponding to a map 2 plunks by 1, and the segment corresponding to from lifts by 1. So this is an example of a graph of a characteristic map of a composition. Horizontal maps are regular, and maps that go down are 2, correspond to the maps to the central manifold. The maps that go up correspond to the class from the central manifold. The oscillation of this function, the depth, is the main parameter n. I will mainly speak in these lectures about the case n equal 1, but I also will touch the general case. There are levels on this graph. This is the 0 level. This is the level 1. This is the level 2. And the deeper the map is, in fact, it will be, after modification of this graph, more and more complicated. I will say right now what modifications we want to undertake. We want to collect together the most deep pits, like this. So if there will be a more complicated characteristic with many pits of depth, say 2, then they should go together in the modified composition. This is again a map of level 1, of level 0. This is a map of level 1, and the deeper the map is, the more complicated it is after the modifications. So before the modifications, all the horizontal segments are just almost regular. But this is temporary. When we modify the composition in the way which is convenient for us, this effect of growth of complexity together with the growth of depth will be observed. Now I say some elementary things about the transition to the logarithmic chart. I recall you that the logarithmic chart is written in the head of the frame. It is zeta equal negative logarithm of z. So z is a chart on the cross section to a separatrix of some singular point. the cross-section with the separatrix is deleted, and the Dulac mapping is a non-univalent mapping on the punctured disk. And when you make the map logarithm, then the Dulac mapping becomes univalent mapping of zeta. This is one of the advantages of coming to the logarithmic chart. There are many other. So I analyze what effects occur when we come to the logarithmic chart. First of all, consider a power mapping. This is the Dulac mapping of a linear set. In the logarithmic chart, it will be a phi. Consider a standard flat map exponential of -1/z. I confess that I was a little bit surprised when I calculated it for the first time. It is simply an exponential map. Indeed, when we pass to the logarithmic chart, the singular point 0 passes to infinity. The standard flat map dramatically pushed the point towards the fixed point 0. Now the fixed point is infinity, and the exponential map dramatically pushes the point towards the fixed point infinity. So a mapping defined by a holomorphic map by a Taylor series with the leading term z. It will be exponential series with the leading term zeta, but the power terms will be replaced by the exponential terms. There is one elementary function which occurs when we calculate more thoroughly the maps 2. And in the logarithmic chart, it is almost obviously an almost regular map. Here is the affine part, and this logarithm may be decomposed in the Dulac exponential series. This series converges. Now, what about almost regular mappings? Their Dulac series, shown here, pass to exponential Dulac series, shown here. Sorry, exponential Dulac series will be an important tool that we will meet all through the lecture today. Now, the most interesting and important actor of this piece is normalizing cochain. I recall you that in the expression for the map 2, normalizing cochains occur. You may forget all the comments that were given about these cochains, and just believe me that upon transition to the logarithmic chart, the normalizing cochains become map cochains defined in a half plane sufficiently right. And what is a map cochain in general? In general, a map cochain defined in some domain is the following object. First of all, we take a partition of this domain by curves that do not pairwise intersect. The domains, the connected, the union of these curves is called boundary of the partition. The connected components of the complementary to this boundary are domains of the partition. In each domain, a holomorphic function is defined. These holomorphic functions may be extended holomorphically to the neighborhoods of their domains. Usually these are epsilon neighborhoods, sometimes a little bit more complicated. Two adjacent, two components defined in two adjacent domains, two domains with a common part of the boundary, are defined together in a neighborhood of this boundary curve. Their difference is called, the set of their differences is called the coboundary of the cochain. And in what follows, requirements on this coboundary will be very important. So when you describe a cochain, you usually should say what decomposition, what partition of, what is the domain of the cochain, what is the partition of this domain, how far the components of the cochain may be extended, how do they grow, how the coboundary behaves, and what is very important, we usually will require some decomposability properties for these cochains that is describe their asymptotic series. So the normalizing cochain passes to something relatively simple. Its domain is the right half plane, probably pushed to the right. The partition is just the partition by the horizontal rays, and the domains of the partition are half stripes of width pi. One of the rays of the partition is the positive real axis. The components of the map cochain are defined in the half strips of this partition, in the domains of this partition, and may be extended in epsilon, the width is not pi, but pi divided by k. What is k? K is the multiplicity of the fixed point of the monodromy map, parabolic germ, of the saddle node. I described in the previous lecture the case of multiplicity 2, and k is multiplicity -1. So in our case, k was equal 1, and now it may be arbitrary. So the strips of the partition have the width pi over k. They may be extended to epsilon neighborhoods of their domains with epsilon written here. It is arbitrary from 0 to pi over 2k excluded. The following requirements are growth. The components have at most exponentially decreasing corrections. So they are identity plus something that exponentially decreases. And what about the coboundary, which I described before? The modulus of the coboundary has an upper estimate of the type double exponent. It is written here, and it comes from the exponential character of the decay of the Écalle-Voronin moduli, which I explained in the last lecture. But right now, you can accept is just as a data. And the last requirement is decomposition, the mappings that make the components of the normalizing cochain, components of F, can be expanded in a common asymptotic Dulac exponential series. It was shown in the table above. So this is the description of normalizing cochains, and we will meet different classes of cochains during the lecture today. The normalizing ones are the most simple. Now, we want to extend the normalizing cochains. I said already when I commented the characteristic of the composition that we want to make some transpositions. So in the picture below, there is an example of a graph of a characteristic of a composition, which is just given to us. We look at the monodromic polycycle, and we combine the characteristic of the correspondence composition of the maps to, from, and almost regular. But we are not satisfied by this form of characteristic. We prefer to have the characteristic like this, when all the pits come together, and then comes a map of zero level. The maps of zero level that are met here form a group, so their product is just one map of zero level. In order to do that, we must extend normalizing cochains to a wider class of cochains, which is denoted FC0. These cochains occur on the zero level. And we want to extend class of almost regular germs to a much wider class of sectorial cochains, denoted by FC1. One, because they are met on the level 1. And they are met here, and they replace the almost regular maps that are met here. So, giving explicit definitions of the classes FC0 and FC1 would take too much time. Later on, I will define FC0, also hiding some parts of the written definition. And I will not give the explicit definition of FC1 today because their asymptotic series require long definition that I will give in the next lecture. So the most important theorem of the theory, one of the most important, is the lower estimate theorem. This theorem claims that cochains of our two classes admit the following lower estimate. On the real axis, they satisfy this inequality. Modulo of the real part is greater than some decreasing exponent. This is even in a standard domain, not only on the real axis. And this estimate holds provided that the upper component of the cochain is not identically zero. The upper component is the one that corresponds to the domain which is adjacent from above to the real semi-axis. Whatever cochains we consider, the real semi-axis will be a part of the boundary of the partition. So we always can distinguish upper component of the cochains we deal with. So this is the theorem about the lower estimate. Now, the properties of the classes FC0 and FC1 that I do not describe allow us to state the additive decomposition theorem for the monodromy map of the polycycle. So if Yulaj's theorem was the major result of his investigation of the monodromy maps of real polycycles, then this theorem is an analog to this one. As I said before, we are in the case when the oscillation of the characteristic of the composition of the monodromy map, this oscillation is 1. That is, the maps to and from alternate in the composition. Such polycycles are called alternate. And the monodromy map of an alternate polycycle is the following. It is the sum of the affine map, a map from a functional cochain F0 from the class FC0, and a finite sum of the compositions of the cochains Fj of the class FC1, exponentials, and multiplications. When I write exponential circle mu, this means that I consider a composition of exponential and multiplication by mu. The corresponding function is exponential of mu zeta. All the cochains F0, Fj exponentially decrease at infinity. So the terms Fj of exponential of mu j have the double exponential rate of decreasing. The larger is mu j, the faster is the decreasing. And therefore, subsequent terms in this sum are incomparable with each other. Any subsequent term decreases much, much faster than the previous one. And the additive decomposition theorem implies the non-accumulation theorem. So I will deduce the finiteness theorem from the additive decomposition theorem. And this is parallel to the Yulaj lemma from the previous lecture, but it avoids a mistake that Yulaj have done. So what may happen? In this formula for the monodromy map, the affine term may be identity, and all the other terms may be zeros. And in this case, all the points will be fixed. But no limit cycles will occur near this polycycle. All the orbits are periodic, but none of them is limit cycle because limit cycle is an isolated periodic orbit. And if the series in the sum in the right-hand side is non-trivial, so either A is affine but non-identical, or some terms Fj with Fj's are not identically zeros, then I will prove that the map has no fixed points near infinity. So let us argue in a similar way as in the Dulac lemma. First of all, if the affine part is non-identical, then the difference between A and identity is greater than some constant, and the sum of all other terms, delta minus A, this is this sum tends to zero, so the difference between delta and identity cannot be zero near identity. This is case one. Case two will be when A is identity and F0 is non-zero. Case three will be when A is identity, F0 is zero, and some of these terms is non-zero, or else delta will be identically zero. So there are three cases. I analyzed the first one. The second one is when A is identity, F0 is not identically zero. And then the difference between delta A and F0 is smaller than exp. Here minus is lost, exp negative nu psi on the real axis, and F0 is decrease no faster than some exponential, so the sum of F0 and these remainder terms cannot have zeros. And the same scheme is in the third case. The difference between delta and A will have a leading term like this. It will exceed this double exponential, and all the reminders will be smaller than this exponential, double exponential, so incomparable with the main term. So this is the proof of the non-accumulation theorem, and this is the major result of all the constructions which are now hidden. So I will reveal them one by one. Now, how the set of cochains FC0 is defined. I will give you almost complete definition, which is sufficient to make the impression of what is considered. I will say what details are hidden. First of all, when we define class of cochains, we follow the same plan as for normalizing cochains. There are 5 points partition with the domain where the map is defined, extension, how far the components of the cochain may be extended, growth, coboundary, and decomposition. So the partition is the product of standard partitions multiplied by real numbers. The formula is written here. The extension is similar to the case of normalizing cochain, slightly modified. The components have exponentially decreasing connections. This is a specific subset of FC0, FC0 plus, the cochains that have exponentially decreasing corrections. And the general cochains may not increase faster than exponents. Coboundary is estimated from above by so-called rigging cochains. A formula for these rigging cochains is written, and this rigging cochain is defined, one rigging cochain is defined in a neighborhood of the boundary ray of the partition multiplied by mu j. So the coboundaries are estimated from above by the sums of these double exponentials, and the main term is the most slow exponential is for the largest mu, for the smaller mu, sorry, mu1 here. So this is the coboundary, and the decomposition is just a decomposition in an asymptotic Dulac exponential series, which was already defined. So this is definition of FC0. And now I will explain from where these simple cochains occur, from where these partitions occur. Affine maps come from the hyperbolic saddles. They are power maps written in logarithmic coordinates. So we consider a normalizing cochain combined with an affine with a linear map, and the corresponding partition is Xi standard multiplied by a coefficient of this map, inverse coefficient. And the rigging cochains are pullbacks of the rigging cochains for the standard partition. So this is a brief explanation from where the details of the definition of FC0 appeared. Now, FC1 is a class of some of so-called sectorial cochains. Sectorial cochains correspond to partitions by rays. The formula for this partition is probably not the most simple. We take the standard partition and apply exponential mappings to it. So this is partitioned by rays that come from 0, and the number of domains of the sectorial partition is finite. And the rigging cochains are pullbacks of the rigging cochains for the standard partition. And the decomposition is much, much more complicated than the decomposition into deluxe series. This is decomposition into so-called super exact asymptotic series that I will discuss in the next lecture. So an important property of almost regular germs was the following. Almost regular germs are completely determined by their asymptotic series. If two almost regular germs have the same asymptotic series, then their difference decreases faster than any exponential on the real axis. And Phragmen-Lindelof theorem for almost regular germs claims that such a rate of decreasing implies that the almost regular germ is just zero. And we want to prove the same for the cochains of the class FC0. If a cochain of the class FC0 decreases on the positive ray faster than any exponent, then the upper component, at least, of this cochain is identically equal zero. I already explained what the upper component is. I will give a sketch of the proof of this theorem if I will have enough time, but now I want to prove another important theorem, lower estimate theorem for the cochains of this class. We used this lower estimate theorem when we deduced finiteness theorem from the additive decomposition theorem, because we wanted to say that the leading term is greater than something and the remainder terms are incomparably smaller than this something. So the lower estimate theorem formulated before claims that cochains of the class FC0 cannot decrease faster than exponentially. So they are greater than some decreasing exponential on the real axis. So the proof of the lower estimate is similar to that for almost regular germs. We take the exponential Dulac asymptotic series sigma for our cochain. We take a partial sum that approximates our cochain with a good accuracy. And there is some partial sum which is non-zero. And this partial sum may be estimated from below by a decreasing exponential. So if there is no such a partial sum, if all such partial sums are zeros, then the series sigma is zero. But in this case, by the Phragmen-Lindelof theorem, the upper component of our cochain is identically zero. And this is a contradiction. We formulated the lower estimate theorem for the cochains with non-zero upper component. So this is the lower estimate theorem. Now I switch to the Phragmen-Lindelof theorems, and this will be the last part of my lecture. And I start with the Phragmen-Lindelof theorems for classical holomorphic functions. The most simple Phragmen-Lindelof theorem is sort of a maximum modulo principle. So I show you the theorem about the theorem about holomorphic functions. A holomorphic function is defined in the right half plane. It increases no faster than some exponential. It is bounded on the positive semi-axis, on the positive real array, and on the of the real axis, and on the imaginary axis. And the theorem claims that this function cannot use the possibility of growth that was provided. It should be bounded in all its domain, and I am sorry for a typo, the supremum of this function f is missed in its domain equals to the supremum of this function on the boundary of the domain. So this is the first version of the Phragmen-Lindelof theorem, improved. Now Phragmen-Lindelof theorem for decreasing holomorphic functions. If a holomorphic function f defined in a right half plane increases no faster than an exponential of nu psi, is bounded on the imaginary axis and tends to zero faster than any exponent on the positive semi-axis of the real axis, then f is identically equal to 0. And the proof is very simple. We take a point in the right half plane where our function is non-zero, and multiply our function by exponential of lambda zeta. Lambda is greater than 0. And exponential of lambda zeta is bounded, have modulo 1 on the imaginary axis. And therefore, it does not change the maximum modulo on the boundary. This function is, function f lambda is bounded on the imaginary axis and on the positive real array. Hence, this function in all its domain is no greater than m, the maximum modulo on the boundary. But in this case, the modulus of f at z0 is smaller than m multiplied by exponential of negative lambda times psi 0. Psi 0 is the real part of z0. And this relation holds for any lambda greater than 0. And modulo f of z0 of zeta 0 is therefore arbitrarily small, and this cannot happen if this modulus is non-zero, a contradiction. So now let us pass to Phragmen-Lindelof theorem for the class of simple cochains for the class FC0. But for general cochains from this class, the Phragmen-Lindelof theorem cannot be explained so rapidly. So I consider a particular class of simple cochains, class NC, like normalizing cochain. Those that correspond not to the product of partitions, but to a standard partition only. And the theorem whose proof I will sketch claims that if a cochain F of class NC decreases on the real axis faster than any exponential, then its upper component is 0. We deal now with cochains, and we want to deal with functions. A cochain may be considered as a cocycle. Better to say the coboundary of the cochain may be considered as a cocycle. To trivialize this cocycle is to find a cochain with this coboundary. For sure, one cochain is already found. This is our cochain. But we want to find a nicer cochain with the same coboundary. And the lemma here claims that we can find a nicer cochain with the same coboundary, and it will be bounded, and its maximum will be estimated through some characteristics of our original cochain. I do not, because of lack of the time, discuss this constant in details, but this is some constant. And therefore, we have a maximum modulo principle for cochains. It is not as good as the maximum modulo principle for functions. Supremum of modulo f is smaller than, equals to the supremum of the modulo f on the boundary. But for the cochains, in the assumptions of the Phragmen-Lindelof theorem, the supremum of the cochain inside is no greater than the supremum on the boundary plus some constant. And this gives us no chance to complete the proof for cochains in the same way as we completed it for the functions, but the same trick may give a weaker statement. The following lemma holds: let F be a cochain of the class NC defined in a standard domain omega that decreases on R plus faster than any exponential. Then for any sector of opening smaller than pi over 2 and with the bisector R plus, and for any positive delta, the following estimate of F in this sector holds. F is smaller than a double exponential with 1 minus delta before psi. And now we apply this estimate to one component of the cochain. This component is defined in a strip which is strictly wider than pi, and the classical Phragmen-Lindelof theorem says that if in a strip that is strictly wider than pi, the holomorphic function decreases doubly exponentially as it is written here, then this function is identically 0. So this is applied to the upper component of F, and we are done. This is what I wanted to tell today, and tomorrow I will speak about super exact asymptotic series. Thank you for your attention.
Thank you.